Jaber from Canada joining us, talking about black boxes and how to make black boxes less black, shedding some light into the black box, understanding why algorithms decide in the black box how they decide and making them more interpretable. And he's doing this on the context of kidney transplants. So very interesting, very relevant topic. False decisions can be very painful and costly, and should be prevented. So Jaber, I look forward to seeing your talk, which concludes our track.
Is it connected? Yeah. Thank you for your introduction. Hello everyone. My name is Jaber Rod, and I'll be presenting the work we've been working in the niche research group at Dalhousie University in Canada. I know this is the last presentation, so I'll try not to make you bored, but I don't guarantee that. Sorry. So just to give you a bit of background. So these days we have like very accurate machine learning models, and the accuracy and the performance of the model is not the issue these days. But what is more important is to tell when the model is not performing well or when the model is making mistakes. And especially this is important in high-stake domains, critical domains like healthcare. So the problem is that the black box model, they don't make any sense in the sense that they don't create logical reasons for their decision making, and we need to explain them out of the box. That's why we call them black box. And so the field of explainable AI was emerged to try to make the models a little bit more transparent. So I'm showing an overview of the pipeline we've developed. I'll dig into like the parts in the next slides, but just to give you an overview, we try to create a set of classifiers, and then we create kind of a surrogate model, kind of like a model, transparent model that would represent the black box models. We call them surrogate, and then we extract decision paths from the so-called white box models, and we would have a large set of decision paths. Then we need to remove noise from the set of decision paths, and I'll talk about noise removal. And then finally, we need to refine this set even more to have a small set of decision path that would be considered as the explanation of the outcome. So let's dive in. The first step is to train the classifiers. The reason we're training multiple classifiers is that every method, every algorithm has its own benefits and its own drawbacks. We call them diverse learning mechanisms. For example, decision tree-based models exhibit bias toward majority classes in imbalanced data sets, but they demonstrate robustness to outliers. On the other hand, neural network models excel in capturing complex, nonlinear relationships within the data. So by learning different models, we could use like the advantages of different techniques. In the next step, we develop simpler models, which, as I said, are called surrogate models. Just to give you a simple background about surrogate models, we take the data and the truth labels, we train the black box model, then the outcome would be considered as a new ground truth, which would be fed to a white box model. It could be a tree-based model, a rule-based model, linear model, a model that can be easily explained to a user. And then the outcome of the surrogate model would be compared to the new ground truth, which was the outcome of the black box model. And that comparison would be considered as the fidelity of the surrogate model. So we try to maximize the fidelity. And we argue that the fidelity of the surrogate model is much more important than the performance or the accuracy of the surrogate model, because the surrogate model is just kind of imitating the behavior of the black box model. So as you can see from the framework, it's not limited to a certain ML model or a certain surrogate modeling approach. So we call them ML model and surrogate model agnostic. But it should be mentioned that the surrogate models should be comparable because we're trying to combine them and creating a set of decision paths. So they should be comparable, meaning that they should be learned on a consistent set of hyperparameters. So in the third step, we create the decision path, and decision path is nothing more than the branches of the decision trees. So as you see there, we have a single decision path for every single branch in the decision trees, and then a decision path would be an ordered sequence of conditional statements, and a conditional statement is simply the variable, the relational operator, and the value of the variable. The variable is the feature in the dataset, of course. And in the fourth step, we try to systematically eliminate the unreliable paths. So I need to explain the quality metrics we're using here before getting into steps 4 and 5. So the quality metrics we're considering for the decision paths are confidence, fidelity, accuracy of the base ML model, coverage, and interpretability. Confidence is basically, it shows how much confident the model is, the base model is in making the prediction. So a confidence of 0 would be that the model says, okay, 50%, let's say, failure, 50% survival. So it's not confident. And the perfect confidence would be 1, meaning that it predicts 100% for one class and 0% for the other. I talked about fidelity and accuracy. Well, accuracy here shouldn't be confused with the accuracy metric. It can be any performance metric like F1 score or area under the curve. Coverage basically gives us the number of instances or the proportion of the instances that are covered by the decision path. And interpretability is inversely related to complexity. And we translate complexity into the length of the decision path and also its relative length compared to the other decision paths included in the set. So having said that, what do we mean by unreliable path? We translate unreliable path into those decision paths that have very low fidelity, confidence, and accuracy. So the meaning of low here can be different in like different classification problems. In a binary classification problem, we could say lower than 50% would be a dummy classifier, right? So fidelity, accuracy, and confidence lower than 50%, we can remove that decision path from the set of explanations. And as the last step, we need to further define the set of decision paths because after noise removal, we would still have a large set of decision paths, and it couldn't be considered explainable or understandable to the user. And the problem of finding an optimized subset would be NP hard. So we need an optimization algorithm. We use the classic optimization algorithm, which would be a stochastic random result hill climbing. I cannot explain everything here, but just to give you a sense of what the algorithm is doing, it's basically choosing a random subset from the set of decision paths, and a path would be considered in the subset if it has more weight. And for weighting the decision paths, we adapted a method from RF plus HC technique, which is a very well-known technique, but this considers accuracy of the decision path as the main factor. What we do here, we adapt the method and change it to the fidelity of the decision path, because as I said, we argue that fidelity is much more important than accuracy. And then we also consider the length of the decision path. So the lengthier the decision path, the lower the chance of the path being considered in the subset. And also we add the confidence metric, which is very important here. And then we try to maximize the fitness function, which would be an average, and with a weighted average of fidelity, accuracy, and coverage of the subset. We also employed some metrics to avoid early stopping and avoid local optima in the algorithm. For example, a stochastic neighbor selection is part of it. So let's put this into action. So I'll explain like a use case of this algorithm. And as a proof of concept, we used kidney transplantation data set. It's a very large data set, and as you see in the TSNE plot, it's a very complex data set, meaning that there are many intercorrelated features, and it has a very stochastic nature. And we have a set of 65 features, so it can be considered as a large data set in that sense as well. And for creating the black box models, we kept a ratio of 70 to 30% training to test. And then we use randomized hyperparameter selection for training the models. And the model, a set of hyperparameters is selected when the F1 score for kidney failure is the highest among the models that have an F1 score of at least 50% for survival, to make sure that we don't have many false positive like choices in the model. And we trained an XGBoost model, a random forest, and a deep learning model. And we try to be diverse in terms of the architectures we're using to see how each of the models would perform. And then as the surrogate model, we're using a simple Cartesian tree, which, as I said, we would have a constant set of hyperparameters. For example, we would have 30 data instances at a leaf node for each of the trees to make sure that all the branches are being generalized well. And let's see some results. So if I look at the models themselves, like the black box models, none of them are performing very well. And that's because, as I said, the nature of the data is very stochastic, and it's difficult to really predict the transplantation. And it gets even worse when we enlarge the time frame. If you saw the slide, I considered a 5-year time frame, which is considered like a very small time frame in this problem. And then when we develop the surrogate models, if you look at the results before removing the noisy paths, we have decent fidelity for training and test set. But if you look at this set of decision paths, we have 585 decision paths, which cannot be considered explainable to user. After noise removal, we would have 320 decision paths, which with kind of the same fidelity. So we reduced the search space by 45% with the cost of 9% coverage loss, which can be negligible. And as I said, the size of the subset should be predetermined by the user before starting the hill climbing algorithm. As you see, if we increase the size of the subset, it doesn't really compromise the quality of the explanation. Accuracy, fidelity, and average confidence are remaining kind of the same. But of course, when we increase the size, then we would have less interpretable model and with more coverage. So this intersection here would be our kind of balanced size for this subset. And if you look at this chart here, we see that with 93% reduction in the explanation size at the end, we will have very small subset of the explanations with the cost of around 50% coverage loss, and all the other metrics are also improved. We also did an ablation study to see the effect of like different elements of the model. And the most noticeable part is that when we do the optimization, then the variance in the accuracy decreases, which is good. And we cannot see very significant effect when we do the noise removal, but it does decrease the search space, so it improves the speed of the overall speed of the optimization algorithm. And this also shows the ablation study on the weight setup. Again, a noticeable outcome would be that if we remove the effect of coverage on the fitness weights, then we would, of course, have less coverage, and it would increase the average accuracy. It would, well, the reason might be that the algorithm would consider kind of redundant decision paths and not paying attention to having like a diverse set of decision paths, which of course would increase the accuracy, but with the cost of losing fidelity and confidence. So let's discuss a few of the results. I cannot explain everything, but I can tell that the first 3 decision paths are kind of compliant with what nephrologists already know. But what I can say as an interesting result, according to nephrology that we work with, is the decision path 4. And if you look at this path, it's in a small one. It's in a small explanation. And an domain expert can say that PCKD, which is polycystic kidney disease, it is, recipients with this disease are not considered those kind of vulnerable to kidney transplantation. So if someone like a domain expert looks at this decision path, the first thing that catches their eye would be that, okay, if I have this value here, I wouldn't say the result would be transplant failure. But if we look at the other values, we see that there are other information that can be considered. For example, the performance status of the recipient. If it's not 100%, it's by the way, it's a 10 value, 10 category feature. If it's not 100%, if it's anything other than 100%, and then the donor is kind of a middle-aged person, more than like 40 years old, and the recipient is on dialysis for more than 6 years, almost 6 years, then with a high quality, if you look at the metrics at the right, with a high quality, we can say that it might lead to transplant failure. All right, so I presented a kind of model agnostic and surrogate modeling agnostic method, explainable AI method, to trying to explain black box models and make them a little more transparent. And so this model is highly flexible. We can adjust the performance metrics. We can adjust the weights to generate explanations for different cohorts of users, for different audience types. As the future work, we're trying to kind of employ the semantic technologies into the framework to kind of enrich the explanations. And there are other paths for exploring in this area. And I think that's it from me. I would like to thank Dr. Taranko for providing the data and for his feedback. And thank you very much for your attention. I'll be happy to take your questions.
Yes, we open up the floor for questions from the audience. Anybody in for a kidney transplant? There's 1, 2.
So thank you for your life-saving research. Not for me, but in general. One question that I had is, you're using a very low complexity surrogate model to explain a potentially highly complex and highly diverse and nonlinear behavior of a model. But then the experiment that you are showing was using a random field or an XGBoost method, and I don't know what your A and N configuration was, probably not that complex. My question is, do you think this would also translate to more complex models where we have really like a deep model with the 500 layers that we cannot explain ourselves?
Well, yeah, so the reason we're calling it black box here is that we don't really look into the architecture. So it doesn't matter how many layers the deep learning model has or how many the subtrees the XGBoost model has. So we look at the input and the output of the model, and we try to kind of create a transplant model out of it. Of course, the transplant model would be a large model because we cannot capture the nonlinearity with a simple decision tree, right? And the reason we're having like steps 3, 4, 5 in the pipeline is to kind of eliminate the paths, or I would call those branches in the trees that aren't worth exploring, really. So we would end up like a small subset of the branches or decision paths that are worth exploring and considering as the explanation. And well, of course, since the white box itself is explainable, it's a decision. It could be a decision tree or a rule-based model. Then finally, this subset of the decision paths would be also explainable.
Sorry, does that mean that for some of the data you can't explain it, and for some you
yes.
can? Okay.
If you saw, like, we had like a loss of 50% for the coverage. So that's interesting. Path to explore. We're looking at the high-quality decision paths here, the part of the data that we can explain. But using counterfactual methods and many different asking what-if questions, it is like another area which we're seeking to explore, and it can try to explain those areas which are less representative in the data. And well, the data set, as I said, is stochastic. There are many different cores that cannot be really explained easily. Yeah.
Thank you.
The second question over there, or?
Yeah, I can make a question. Thank you. Initially I was volunteering. I thought there was no one. So can I ask you please to go back to slide 11?
Yeah. Oh, it's not fast.
Okay. So
yeah,
the first
there
question.
You can do that from there. Okay. Yeah. Oh, sorry.
Okay. Yeah. So here, after you aim to remove some paths which are, let's say, relatively long, right?
Yeah.
So how much did you investigate actually building a surrogate model, a white box model, that is relatively simple and can only yield or provide shorter path?
Yeah, it's an interesting question. For the simplicity of this experiment, we only use like a cart decision tree, as the architecture of the model. But there are many other different methods for creating that. Like the name of the methods are not at the top of my head, but as you said, there are some methods that can generate like smaller decision trees to capture like nonlinearity better. We can also explore methods that would generate rule-based representation. So the reason we would generate rule-based representation is that we can have subsets. We're not kind of limited to one single decision tree. We could have like different subsets, and then we could kind of aggregate the subsets based on like the quality metrics and length of the rules. But yeah, so this is if I bring the future work slide, this is one of the paths we're going to explore. Yeah, and this is agnostic to the surrogate modeling approach. Yeah. So the cart decision tree can be combined with any other method that would generate a decision tree.
Another little question, just a curiosity. What's confidence? Well, how did you quantify confidence? Uncertainty?
Yeah, exactly. So it would be a prediction probability. So the metric we use for calculating area under the curve, prediction probability. So if the prediction in the case of a binary classification is the prediction probability it's 50% for one class and 50% for the other, it's zero confidence, I would say.
Okay, thank you.
Any other questions to Jaber? If that's not the case, then we conclude the track 5. I hope you had a good time today, and I see you around for the apéro. Don't forget to vote for the posters. I think you still have a couple of seconds, minutes to vote your favorite poster. And yeah, thank you for coming to the Swiss Data Science Conference, and see you around at the apéro and latest next year. Jaber.